Hello, my mVAC fan club. This is Sean from Having Fun Repairs, and I wanted to do an exclusive video, or at least a time exclusive video for all of you in the fan club, going over test equipment. I know a lot of you are seasoned technicians and engineers, but some maybe not so much. So I want to give an opportunity to teach some things that I learned about 20 years ago when I first started learning about electronics and went through training in electronics principles and how to use test equipment. Forgive my voice a little bit, I'm a bit underneath the weather, but up in this first video that I'm going to release to you for a good while before I ever post publicly on my own channel, I will keep this unlisted, to say the least, for a good long while until I get more videos built up. But I want to go over multimeters. Now, a multimeter or multimeter, depending on how you pronounce it, can serve a wide range of functions. As a matter of fact, they also come by many names to begin with, such as a volt-ohm meter or a digital multimeter, or DMM for short, or just simply referred to as a multimeter or multimeter. Now, I'm going to set these two aside for a second. What we have in this case is a volt-ohm meter, and as the name implies, you see it there, it's used for measuring voltage and resistance. Now, this is a triplet electronic I-66 is the model number. This volt-ohm meter was used by U.S. forces in World War II. It can be used with mains AC or a dry battery 4.5 volt DC source. It comes with a lovely schematic in here, which will be good for when I go through and try to restore this and make it operational again. You can see on the switch setting, you have your AC measurements over here, DC down here, resistance measurements over here, and then it looks like you have a high impedance AC measurements over here, assuming that you might have to couple a 0.5 microfarad capacitor to your measurement lead. I'm not too sure. I'd have to look at, find a book and figure out exactly why this was added in, but assuming that it has to deal with certain AC measurements needing a capacitor coupled to the tip of your positive lead. This is a very nice device. When you would turn it off, you would need to zero your meter, or say turn it on and not connect it to anything, not make a measurement yet. You would zero your meter, and then you would attach your leads and hook it up and get a very accurate measurement. Now, a volt-ohm meter is actually pretty popular to a lot of people who work on electronics, and that's because they traditionally, at least you can research a bit of this yourself, from my understanding, they are extremely sensitive to whatever device is under measurement, and so you get a great amount of accuracy when using such a device. Now again, at some point in time, I'll restore this guy on my channel, but for now, we're going to set it aside. And left my mat a bit dirty. Not to worry, I'll clean that up later. Anyways, here we have two examples of digital multimeters. This one was a Craftsman one. I think this was given to me by somebody many years ago. Most likely bought at Sears, or maybe even carried by Radio Shack back in the day. This was the first multimeter that I owned, and a lot of my earlier videos was the primary multimeter I used. I actually prefer the leads to the leads that are on this fluke because they're made out of a rubberized material that is typically a lot more heat resistant than this kind of PVC-ish, less malleable, this stiff material that comes on a lot of new leads, which is very easy to melt in a lot of cases. Say if you have a soldering iron laid on it, which you know, if you're not paying attention to what you're doing, it could happen, right? Now, why would you choose one multimeter over another? Well, David Jones over at EEV blog goes into a lot of metrology and you know, the arguments over which multimeter is best. But I traditionally stick to a fluke because that's what I use at work. Now, I know based off of years of use that I could trust the accuracy of a fluke multimeter. Are there more accurate multimeters? Absolutely. And I also trust the metrology standards that were used to develop this multimeter as well as it being made in the US and the warranty and everything else. Now, the main difference between these two multimeters, I mean, this is a Craftsman. It's not going to be built, in all honesty, to the same standards that this one right here is, but it is going to give me some measurements that, you know, in a pinch, if I'm toting around a bag while working on something and I can't quite fit this in there, I might throw this one in my bag just to make some preliminary measurements. Now, this multimeter allows us to do AC. We can look at ADC, so we have amperage ranges as well. We could check batteries. We have a diode check function. We have a resistance check function. And then we have our volts DC as well. So AC measurements, amperage DC, up to 10 amps, which requires moving a lead over to do that. Okay. Actually, I think you have to move the positive lead over, so forgive me for that. But battery checker function, resistance 200 to 2000 K, and then volts DC, we go all the way up from 200 millivolts to 600 volts DC. Now, what this fluke affords me, and the reason why I bought it, is because not only do I have volts AC, volts DC, millivolts AC, resistance, a continuity check, diode check. We can measure amps AC, amps DC as well. But it also gives me, underneath the second functions, to do frequency over an AC measurement, and as well as this diode, capacitance over the secondary function as well. Now, I don't traditionally use these other two functions, so if you want to know more about them, you can look up the book. But I do want to kind of go over some of the things on this multimeter and how to actually make proper measurements with it. Now, because some of these demonstrations I will be having my hands near mains voltage or a voltage, I'm going to remove my wetting band because it is conductive. In a lot of my videos you see me leave this on, typically with DC circuits, especially low voltage DC and low amperage. I'm not too concerned. I keep my hands relatively out of the way. But it is a good practice regardless to always remove metal objects from your hands when working on electronics. As a matter of fact, if you wear glasses like I have to when I'm trying to actually focus in on things, to have a band around the the rims on your glasses to keep them from falling off your face and into whatever electronic device you're working on. Or if you wear a necklace, you probably want to take that off as well. You've seen in a lot of my videos that I have formed some bad habits from working on electronics for so long. But anytime I'm dealing with mains voltage and high amperage, or a combination of either one, or high DC voltage and high amperage, and a combination of either one, I will remove my ring. The risk is just too substantial. But like I said, don't have the bad practices I formed, have good practices, keep yourself safe, remove all metallic objects that dangle or can fall into electronics. So let's first talk about our AC measurement function. I'll flip over to it. Now I have a plug that goes to the actual power cord that goes to my DC power supply, and we're going to take a measurement ground to ground, and then on the left side should be my hot lead. We can see that we are measuring AC voltage. Modern traditional AC mains coming into your houses in America is around 120 volts AC. It used to be a bit lower, around 115 to 117, but there was a change many years ago, I think around 30 years ago, where the voltage was increased slightly to draw current down. But depending on where you live, your mains voltage could be 220 or 240, okay? And then there are some applications here, even in the state, where you need 2 or 3 phase AC at a higher voltage as well, such as 220 or 240. Now that being said, I'm going to remove this positive lead, and then I'm going to switch to this Hertz function. Now, it doesn't take much to make this type of measurement. As a matter of fact, even with my ground probe plugged into the ground, because of essentially inductance, I can measure the phase of the AC coming in, and we can see that it is 120 volts AC at 60 Hertz. So that's one good use for this Hertz measurement. But let me show you another one. Up in the left hand corner, you can see that I have my SIGGEN turned on and set to 10,000 Hertz. We're going to drop the amplitude down to 1 volt, peak to peak. And I have the leads coming off of it, heading down here to my mat. I still have my digital multimeter set to the Hertz function, which if we were to look inside our Fluke multimeter book, we can see that we have a range of 5 Hertz to 50,000 Hertz. So this is in a frequency range in which I can actually measure. Now again, if I was just to touch the negative lead from my SIGGEN that's going to the ground of that BNC connection to the negative lead going to my digital multimeter, you can see that AC, that is mains AC, the frequency that is coming in at, being inducted onto the ground. That doesn't mean that there's an AC voltage per se on this ground. This is safe to touch, okay? That's going to be extremely low amperage, and that's why our devices traditionally are built the way they are to keep us safe. As you can see, as I touch it, it does change though, because I am creating a load on this this ground line. Now, that's not what we're supposed to be measuring though, which is primarily why you need to use your negative and your positive lead coupled to your negative and positive line from wherever you're trying to measure your frequency. If I was just to attach the positive lead, you can see that again we're kind of all over the place, and we're not measuring what the device is actually outputting. I'm going to turn off channel 2 real quick. So let me attach the negative lead as well, and there you go. We're seeing that measurement of 10,000 hertz. And we can actually test the range of our digital multimeter. So if I wanted to, I could increase this to 30. I also needed to increase my amplitude a bit, but now we have a measurement of 30,000 hertz on our digital multimeter. Let's do this again. Let's go to 40,000. We may need to increase our amplitude again. There we go. We now have a measurement of 40,000 hertz. And I could do this on and on, but to put it simply, having a frequency, the ability to have a built-in frequency counter into our multimeter can come in handy when diagnosing things on a circuit board, especially if you have a device such as a local oscillator generating a frequency within the range that your digital multimeter can actually check to measure it. I will say most devices I work on are up in the megahertz range. However, there is the ability to make certain measurements with some devices within the range that is allowable on my digital multimeter. Now on to our DC measurements. I have the device selected up for a DC measurement, that is direct current versus AC alternating current. Flows in sinusoidal waveform. DC direct current. I have my benchtop power supply plugged in, set to 1 volt, and only increase my current up to where it allowed me to produce a volt. I'll explain why here in a second. Now typically when you do a DC measurement in circuit, especially concerning where the circuit negative rail is at, or return, you're going to put your negative lead, say it's a battery powered circuit, onto your ground rail, and then positive lead to whatever point is on the device for testing. So you can see here that on the negative lead and the positive lead, I am measuring the 1 volt that I am generating from my tabletop power supply. Now something I want to demonstrate for you, and this is a little bit of electronics principles. Voltage is at its lowest when current is at its maximum. Or basically what that indicates or means is your voltage will be at the lowest measurement when there is a short somewhere in your circuit. We can demonstrate that, and this is the reason why I turned the current only up as far as being able to generate 1 volt. If I was to short out my positive and negative lead coming from my power supply, you will see that that voltage drops. Now I'm not measuring anything with it shorted out. I don't recommend that you do this at home, but simply put, that's how you, that's a little bit of DC theory for you, which is helpful if you're troubleshooting and you're going from, say, a ground rail on your circuit to a test point where you're supposed to get 1 or 2 or 3 or 5 volts or whatever it is, and you don't see that voltage. Somewhere there's probably a short, especially if the device is powered on, meaning that that voltage has a direct path to ground, so current is at its maximum, and so voltage under measurement is at its minimum. There are some other practical applications for a DC measurement as well. I've taken two 220 ohm resistors and twisted the leads of both of them together to essentially make a voltage divider. I'm going to attach one side to the negative lead going to my DC power supply, developing 1 volt. I'm actually going to increase that voltage up to, let's do 3 volts. That's pretty typical of most common toys, having a 3 volt power supply or power source. And then I'm going to attach my positive lead to the other side of these resistors. Okay? And let's see, can I weigh this down with something? Sure. Use this book to weigh it down for a second. Now, from negative lead to negative lead and positive lead to positive lead, I measure that 3 volts. Roughly, it's a bit over 3.06 come from my power supply. That is coming across, being generated from the power supply. Okay, but because I've made a voltage divider, I can measure the voltage drop between each resistor. So we've got 1.5 coming across this resistor, and then if I go between here and here, I should see another 1.5. So why would something like this be important? Well, I kind of did a very small diagram for you, but let's consider our circuit. We have a 3 volt power supply. Let me turn mine back on. There we go. And we have a test point on our positive rail seen right here, as well as two 220 ohm resistors that are put in series with this circuit. Now let's say that I am expected to measure 3 volts right here at this test point, and say we've drawn another one here, TP2, I'm expected to measure 1.5 volts here. Have you already started figuring out why this is important? I've got my 3 volts, and I've got my 1.5, but what if this was missing? Well, then I have a resistor that's bad in this circuit. I would probably also, if a resistor was burnt out, not have this voltage here at TP1. Or let's say that our resistor values have drifted significantly. Well, measuring between these points could also indicate to us which resistor has gone bad. So that way, before we remove this resistor out of circuit and do a resistance check, I know which resistor I should probably remove first. Let's do another practical application. In this circuit I've made, I have a 16 volt 1000 microfarad cap. The negative lead of the cap going through a 220 ohm resistor. I have my positive lead of my 3 volt power supply going to the positive lead of my capacitor, and the negative lead of my power supply set to 3 volts going to the negative lead through the resistor into the negative lead of the capacitor. Again, in circuit, say there was a test point over on this side, I should still see the 3 volts. As a matter of fact, I do. It's, my power supply is a little bit low. I can bump it up. It's at 2.9 now. It's at 3. But there goes my 3 volts. But I want you to see something. If I was to test this on the negative lead, am I reading any voltage? Absolutely not. Should I read voltage? Absolutely not. And here's the reason why. A capacitor's purpose is to pass AC but block DC. Capacitors themselves are used in a wide range of applications, such as could be used to and designed for key rolls and filters and amplifiers and power supplies and many additional circuits, wherein you may need to decouple AC hum or filter out frequency or noise off an AC signal. which you know, if you want to keep a nice AC voltage, which you know, you may want to regulate, say in a power supply to a DC down voltage down the line. All those things are important. Equally very important in audio circuitry, because it helps clear up the audio circuit and get rid of hum out of your audio lines. And you know, if you have an LC tank circuit where you might have a mains voltage pretty close by to the output audio source, it allows you to get rid of inductance from those lines onto your audio out. As a matter of fact, don't have a way of plugging this up into a power supply anymore from this little wall wart that I've completely demolished, but you can see several capacitors on here rated high at or higher than the mains voltage. So you see a 400 volt 10 microfarad cap, 400 volt 10 microfarad cap again over here. But towards the output, you also have a capacitor rated for a much lower voltage, 16 volts, 220 microfarad, in line with this inductor. Again, I did mention LC tank circuit, so we have an L inductor, which does the opposite of what a capacitor does. An inductor allows DC to pass through, but blocks AC. So an inductor is good for getting a straight AC voltage off of your DC line. You don't want to have a varying DC voltage because that's AC. And then some applications you don't need your DC voltage to vary at all. But anyways, kind of rambled on there a bit. No way I'm going to plug that up and test it because it was broke anyways. And but yeah, hopefully this kind of goes over some of the importance of DC measurement functions. And as a matter of fact, you know, if you were to do a resistive or continuity test across capacitors, hopefully this enables you to understand what you should be seeing if a DC voltage is applied and there is power in circuit. Again, we'll get into resistance checks a little later on, but there are definitely, those measurements are not done with a while the circuit is energized. That would be a big safety risk for you. Now, I'm not going to give a practical application for this next setting, but this is your millivolts AC or AC voltage measurement between 6 to 600 millivolts, that with its secondary function you can DC couple to DC voltage between 0.1 to 600 millivolts. So you're talking about very low voltage measurements. Okay, that's essentially what this one is used for. Now let's go into resistance measurements, or ohms setting. Again, probably something you're very familiar with by this point. But with a resistance measurement, we can determine the ohms of the resistance of a component that is in circuit, measured in a value of ohms. So this is a 220 ohm capacitor, resistor. I'm measuring 221. And so is this one, measuring 219.8. So they're both fairly close. Now, if I was to twist these leads together and put these resistors in series with each other, then my total resistance will be the sum of both resistors. There you have it there, 440 ohms. However, if I was to take these resistors and put them in parallel with each other, and make the same measurement, what do you think my value would be? My measurement would be? Look at that. It is half the value of the resistance for each resistor. So 220 divided in half is 110, right? Now you could swap out resistors for different values to make a completely new circuit, or sorry, resistance. Make a completely new, or I'm fumbling over my words here. But anyways, if you say you needed a 100 ohm resistor in circuit and you didn't have a 100 ohm resistor, you could take two different resistors, say two 200 ohm resistors, put them in parallel, and that would make a form, resistors in parallel would give you a total resistance of 100 ohms. Sometimes this is beneficial for certain circuits, but again, it all comes down to your diagram and what you're measuring. Resistors in series versus resistors in parallel to determine the total amount of resistance within a circuit. And that is good information to know when you're troubleshooting. So if you're on a schematic and say, let me draw something. You had a test point between here and here, say TP3. Again, no power should ever be applied to any device when making a measurement in resistance, okay? Because you're using the internal voltage of your digital multimeter to couple through your circuit to make that measurement. So if you had live power going through here and then you took your leads and applied an additional power, you're probably going to get a bit of sparkies and no funny funnies. But anyways, this was in series, and if I was to measure between here and here, I would have 440 ohms. And then if I was to draw my diagram like this, plus minus, and let's say I had a resistor here, okay, 220, and a resistor here, again, 220. Now they're in parallel versus series, and the resistance across my circuit will now be 110 ohms. Good thing to know when you're looking at a schematic diagram and you see this or this, you should be able to predetermine through Ohm's law or other functions what your measurement should be roundabout if you're doing a resistance check to determine failed components. An app I often find myself coming to because it's just so very handy and I don't have to do math as a electrode doc. But anyways, there is an option here for resistor series versus parallel. If I enter in the desired value I'd like, 220 ohms, then in series I could put a 120 ohm and a 100 ohm resistor to equal out to 220 ohms, or just one 220 ohm resistor, or in parallel I can take an 820 and a 300 ohm resistor, put them in parallel, and that will also come out to 220 ohms. But just something for you to check. As a matter of fact, if say you just happen to see two resistors in parallel and say one was a 1K and the other one was say 450 ohms, well then the total resistance would be around 310 ohms. Pretty fun things to think about when you're troubleshooting a circuit and you've got resistors that are in series as well as parallel. There are calculations that you can do, to know what you should measure when doing this type of functional test. And I'm pretty sure there's a whole lot more resources online that you can read up about and actually understand how to do the math and everything. Again, this is just really an introduction to using a digital multimeter. However, resistance measurement isn't just limited to measuring the amount of resistance based upon your resistors that are in circuit. It is also good for testing capacitors. Now, why do I say that? Well, a capacitor stores an electrical potential. This is a 10-volt capacitor at 470 microvolts, but when I put my fluke into resistance, watch what happens. Black lead going to the negative side of this capacitor. This is a polarized cap, electrolytic. Positive lead to the right side, and we should see this capacitor. Actually, as a matter of fact, let me demonstrate this first. There is nothing on this capacitor. Okay. 0 voltage. Now when I put it over to resistance and attach my leads, you'll see that this capacitor starts to charge until it gets to that OL state, and then it would start to discharge. Now if I was to put this back to my DC voltage, we can now see that we have an electrical potential of 0.6 DC volts stored on this capacitor. So why is this good for testing capacitors as well? Well, a capacitor should charge and discharge. As a matter of fact, while a capacitor is charging, so long as it's not leaky, it should get to that OL state. Otherwise, it's just going to constantly measure as a resistor. A leaky capacitor will measure as a resistor versus charging and discharging, as you see with the ohm setting measuring across our capacitor now. And if I was to reverse the leads, I don't recommend doing this, you can also see that it's starting to discharge. However, because this is a polarized capacitor, that discharge is not meant to occur. You're not meant to apply a DC voltage to the negative side of that capacitor. Again, we still got, you can see that the voltage actually inverse when I switch the leads, but now we're at a negative 0.6 potential. And if I short out the leads and check again, we're back to 0. Anyways, that's a good tertiary function for a resistance check, is to see if your capacitors are charging, and if they get to the range of registering OL, or out of range, and then to see if they discharge. But if they measure as a resistor, then at a constant resistance value, then that capacitor is most likely bad. Or say it's not just leaky, it's actually all the substrate that's used inside of the capacitor, say that this all shorted together, well, then you would just get, let's tie our two leads together. It might do it. Let's measure again. Look, shorted capacitor. So we have 0 resistance. Continuity tests, our next function on our digital multimeter. The continuity test, you'll see a lot of YouTube, people on YouTube with similar channels calling it, a beeper, whatever. But anyways, it is a good test when you're just wanting to measure between continuity between different passive devices in circuit. Now again, this is another test in which you do not have power applied in circuit, okay? Because you're using the internal battery voltage and the application of coupling your leads to the circuit to make this continuity measurement. And it is also extremely wise to go to, say, your Fluke or whatever book that came with your multimeter to see the ranges allowable to get that audible tone. We get continual beep at less than 20 ohms, and it turns off at greater than 250 ohms. Now, so let's say that these were in a circuit board. I've got my 220 ohm resistor, 220 ohm resistor, and then my 47 microfarad 10 volt capacitor. This going to the positive leg, and this over here being the negative leg. Now, if these were in circuit, say that there's another device down here, I can measure from here to here. Obviously, I'm going to have continuity, right? But between here and here, I would have a measurement, but I might not have an audible tone. As a matter of fact, I'm seeing 220 ohms resistance. And then from here to here, I get 440 ohms resistance, okay? Now I want to show you something that's a bit interesting if you don't understand circuits too well. Watch what happens when I initially put my negative lead to the negative lead of the cap and my positive lead to this side of my first 220 ohm resistor. You might have initially thought, oh no, we've got a shorted cap. But did you notice how once that cap charged up, that continuity disappeared? This is why it's very important to understand a bit about passive components and what they do in circuit. Again, until this capacitor fully charges, I have a continuous path to ground, essentially. Now I can discharge the capacitor and it will beep until it charges back up, and then I can reverse and go back and do the same thing. But the primary intent of demonstrating this to you is that way you understand that if you're taking a if you're using a continuity test in circuit and you're not entirely sure where you are in your circuit and you have continuity at one point and then it disappears, you might want to check to see if you have a capacitor in circuit that you just charged until voltage became at max and we were not allowed to draw any more current through the circuit. But anyways, there goes some good functions for you concerning our continuity tests. And then a lot of times when people also replace capacitors in circuit, even when you get to like a diode test or a continuity test, until the capacitor cools down, it's probably not wise to use any one of these functions for your initial testing. Now on to our next dial position. We're going to do diode. Now a diode is basically designed to allow for current to flow in one direction but not the other. So essentially you have a forward biasing voltage and a reverse biasing voltage. You can read more about those kinds of things online if you care to. But essentially, on one side of our diode is the anode, that would be the positive side, and the other side is the cathode, that is the negative side. The cathode is usually indicated by a stripe on one side of your diode. We have, for demonstration purposes, I have 3 diodes sitting here. We have a 40 volt 3 amp Schottky diode. We have a 400 volt 1 amp 1N4004 rectifier diode. This one, the part number was 1N5822. And then we have a 100 volt 200 milliamp 1N4148 switching diode. And every different type of diode is essentially going to give you a different measurement. Now again, you don't do a diode measurement while the device is powered up and voltage and current is applied in circuit. You do it with the device powered down and disconnected from whatever source voltage. But you can see as I go across the diodes, positive to the anode, negative to the cathode, that our switching diode gives us a voltage drop of 0.588. The rectifier diode gives us a voltage drop of 0.573. And the Schottky diode gives us a voltage drop of 0.211. Now, if I was to reverse my leads across these diodes, we should not measure anything. It should all be out of range. A lot of times you can do diode measurements while it's in circuit but not powered up, just like you can with resistors, so long as you know the value of them and whether they're in series or parallel, because that will mess up what you think your total resistance will be. However, when you're using a diode test, if that component is in circuit, sometimes you'll get polarity both ways around. And that depends on how it is in circuit to be able to test it. So a lot of times what you need to do is you need to desolder one side of your diode. Usually the anode is probably the best one. And then take your measurement again. And then, or completely remove the diode out of circuit. To try and demonstrate this for you, I have now put my switching diode in circuit with my 220 ohm resistors and my 470 microfarad 10 volt capacitor. I have the cathode of my diode going to the negative side of my capacitor. I probably should twist this on just a little better. Yeah, that should be good. And the anode side of my diode going through my resistors to the positive side of my capacitor. Again, in diode mode, I take a measurement. And we're not seeing too much of a change for this diode. We're still getting, 0.588 of a voltage drop. But watch what happens this time when I reverse. If I was to reverse my leads. Did you see that? I had a voltage drop showing continuity over this diode until the point that my capacitor fully charged up. Again, something that you need to be aware of. And if I was to reverse the leads back over again, watch what happens. Did you hear that continuous audible tone? Until which case this capacitor discharged and recharged back up, and now I've got the correct voltage drop reading, or at least one I would expect for a switching diode, being about 0.588 in or out of circuit. However, like I said, this doesn't always hold true depending on the circuit and the diode used concerning what you would measure across the diode. A lot of times in circuit, that voltage drop is going to be different. So that's why I would refer you that if you don't know what type of diode is in circuit, that you remove it out of circuit. You use your diode test to measure the voltage drop, and then get yourself a box of diodes, okay? And as long as you know the voltage that is in the circuit and the amperage that that component is going to draw, you can go ahead and kind of determine the type of diode you need by testing their voltage drop out of circuit. This is going to bring us now to our capacitance function, where I can test the capacitance of a capacitor, such as this 470 microfarad 10 volt cap that I've removed out of circuit. If I use this with my multimeter, again, no power applied component for the component in circuit, removed from its voltage source, turned off. Now, traditionally, what you want to do is measure your capacitors out of circuit, either by removing a leg or fully removing the capacitor out of circuit. When you are measuring capacitance, you should be very close to the rating that is stamped on the capacitor. This is a 470 microfarad capacitor. Now you can see I am measuring 455 microfarads. That is fine. Imagine there will be some slop depending on the manufacturing process, but I will say, based off of experience, that when a capacitor is measuring, now we're at 460, 450, anyways, if a capacitor is measuring slightly below its value, that is okay. But when it's measuring above its value, you might have a leaky capacitor starting to act more like a resistor. So, first off, remove the component out of circuit, then do the measurement. Now, you can measure them in circuit, but you need to keep a few things in mind. Let me demonstrate. Here again, I have my capacitor in circuit, that switching diode and the resistors. I will take my negative lead, put it to the negative side of my capacitor leg, and the positive lead to the positive side of my capacitor's leg. If I can get on there well enough. Might have something not quite right. Let me tighten it up. Alright, here we go. Notice how that reading is now a lot higher. That is because this capacitor is now in circuit, and now I have to battle basic limitations of this type of measurement in circuit with resistance, and let's say if another capacitor was in there, other capacitance. Okay, this will increase your measured value, and you'd probably think, oh, maybe this is a leaky capacitor. No, it's probably still a good capacitor. You're just measuring it in circuit. Now it's a good check just to say, hey, am I reading capacitance? Yeah. Is it a bit above 470? Yeah, it's not below. Most likely that's a good capacitor. But, you know, if it's way off or like super way off, you might want to pull it out and test it, as well as doing switching over to your resistance or ohm measurement and checking just across the leads to see if it charges up and goes to OL. Now, another thing to be concerned about is what if you had another capacitor in circuit with this capacitor? Let me demonstrate that for you real quick. Now I've got two 470 microfarad 10 volt capacitors in circuit with everything, and when I take my measurement, we are now getting a capacitance reading of 1,000 microfarad, essentially. So when you make a measurement in a circuit that has many parallel or series capacitors, you need to be aware that that's going to change the sum total of capacitance in circuit. And to provide a bit more clarification on this, I have now removed both of these capacitors out of circuit. Let's check the capacitance of both of them. We have for a 474, so that's really 476, really close to 470. And this one that we've been messing with a lot, 467, 454, you know, lower. Nothing is egregiously out of range in my opinion. But let's now tie our leads together. We'll say roughly 470 each one. Now let's check it again. .470 and 470 is what? 77 is 14, right? 44 is 8 plus 1. So 940 microfarads, and we're essentially there. So just as an extra demonstration to show you. Now we're going to get to our last two measurements on our digital multimeter. Excuse me. Current with AC measurement and current with DC measurement. Now essentially they're the same thing, but for demonstration purposes and without having to go to my isolation transformer and hook up some things to keep myself a bit safe, I do not want to measure current over AC to demonstrate in this video. I will do it over DC though. And did you see that little lead notice? Well, that's because we actually have to change our leads around on that multimeter. So I need to take my positive lead out of this voltage input, and I need to take it over to my amperage input, where I have where it's 10 amp fuse between our common and measuring for amps. This is how I set up for a current measurement. Now, I want to preface this, in my opinion, this is the most dangerous measurement that you can make in a circuit. And the reason why I state that is because these measurements are done while the circuit is under power. Whether it's mains or DC, the circuit has to be live. Okay? And then secondly, your leads must become in series with this circuit. So, for demonstration purposes, let's say that these two resistors were in circuit together, and I had a negative rail here and a positive rail here. I would have to disconnect these out of circuit and put my leads in line between the components to measure the current draw between them. Okay? And while you have things disconnected, remember what I said earlier? Voltage is at minimum when current's at maximum. Well, right now current is not at maximum because the circuit is not completed. So voltage is at maximum. So whatever potential is stored here, say positive lead is on this side, stored here, if I were to touch it with my finger, if I'm not being careful, now I am a path to ground. And depending on the amount of voltage and the amount of current, it can be very dangerous. So you need to exercise quite a few precautions. Now, I have my DC power supply set to 3 volts. Current at minimum is possible, just enough to allow me to get up to 3 volts. Obviously, these are not connected to each other. But if I was to take my leads between the two, I can measure the amount of current between the two leads. And I get 135 milliamps. Now, I want to take my resistor and I will clamp it to my negative lead. My positive lead is still out here. Now I want to know the amount of current draw occurring with this 220 ohm resistor. Let me get this up here. That might have been outside of video recording range. Now I want to measure the amount of current with this resistor in circuit. And I get 14 milliamps. You see how that current dropped? Current limiting resistors are used with LEDs, right? To lower the current to prolong the battery life of, say, your LED flashlight, and also to prolong the life of your LED by dropping the voltage, because again, as we measured earlier with DC voltage, you have a voltage drop across the resistor. Now I wonder if you have two resistors in a circuit. I'm going to turn off my power supply for a second. And let me put this other resistor in. Turn back on my power supply. And we're back at 3 volts. Wonder how much current is being drawn between these two objects. 7 milliamps of current. And there you go. So current measurements have its purpose, and yes, depending on the schematic you have and what is listed on that schematic, you can do a current measurement, but you must exercise precaution. I cannot foot stomp that enough for you. I also want to foot stomp that you need to know the particulars of your device and its rotary switch settings and its allowable inputs and tolerances. Knowing what their rated values are should keep you from ever blowing this 10 amp fuse or blowing out your test leads. Obviously, some extremely high voltage and high current measurements cannot be done with certain multimeters. As a matter of fact, you have voltage safety probes, a different type of probe used for high voltage circuits that you would use for those type of measurements, not something like this right here. If I was to look at my DC current measurement, it allows me to measure a current of 1 milliamp to 10 amps. Greater than 10 amps to 20 amps, 30 seconds on, 10 minutes off. If I'm greater than 10 amps, the display will start flashing, and if I'm greater than 20 amps, OL is displayed. So we at least understand right now that I'm probably going to run into some issues once I start getting above 10 amps. Hello, there's a 10 amp fuse. I go above 10 amps, I'm probably going to blow this fuse. That should save me from hopefully not destroying my leads, but will definitely save me from essentially ruining the internal circuitry of my digital multimeter, which I do not want to do. So if you're taking a current measurement or any measurement in general, know what it is in circuit before you use your digital multimeter. Okay? Know what your DC voltage is at the test point, if at all possible. When it comes to current, read any product available for that device so you know how much current draw is in circuit, so you're not going above the rated values of your digital multimeter and destroying it. And also, not just destruction of your device, but potential shock and hazard for yourself. Well, my Mate Vince fan club, this is going to do it for our humble multimeter here in this video. Hopefully you've been able to take something away from this demonstration. going over the functions of the multimeter as well as the application with components in circuit and out of circuit. Now there are so many more things that I could cover, and there's a wealth of knowledge out there on the internet. I just didn't want to do it all in this one video because it would be extremely long. That being said, I don't know what I'll do with this video in the future. It is a timed exclusive for you. I may publicly release it at some point on my YouTube channel, or I may put it behind a paywall and start up a Patreon. Primarily because I am operating Having Fun Repairs as a business in the States, out of Oklahoma. And when you've gone through as much training, education, certifications as I have, there are certain things that you just realize you don't necessarily do for free. But I don't mean that in a negative connotation. I just mean to state it as it is. That being said, if you like this video and this content, comment down in the comment section on Facebook as I release it on the page. And please consider subscribing to Having Fun Repairs, my YouTube channel. I realize this is my main Vince fan club. I'm not trying to take away from anything that he does. His channel is phenomenal. And personally, I consider Vince a friend. But that being said, I'm not trying to take away from anything he does, any monetary value that he gains from his channel or anything. I'm only releasing this here as an appreciation, as a timed exclusive for you all in this community, because I do know that there are a lot of people in this group who might not have the experience that I do, or the education or certifications. So this should be able to help you, and I will do more videos like this with other test equipment that I have in my office and how to use them in their general application with making measurements on a given device. Now, that being said, if you do like it, yes, please consider subscribing, or if you just want to help out my channel, there is a PayPal in the description. Absolutely no obligation whatsoever. The one thing I do want to point out, if I haven't mentioned it already, if you go to my Google site, link in the description, I have how-to guides concerning different things like soldering to component swapping if you don't have a like for like on a circuit board. That's stuff that I have built into Word documents that's released to the public, and that's going to be general information. Now, I haven't worked on many more because I just don't have that time with 4 kids and a full-time job, and as well as making content and more schooling because I'm working on another degree. But that being said, please take this video for what it's worth, discuss it. If there's something somebody with more knowledge than me wants to add in the comment section, by all means do. I have learned that the best way to learn is to be a teacher. I used to instruct as well electronics in my career field at a schoolhouse down in Mississippi. But anyways, thank you for watching. Take care. Goodbye.
Bark?